We physicists have waited 100 years since 1916 for this photograph. It is a region black holes might just be one of the most fascinating and mysterious phenomena in the universe. They are massive beasts in terms of power, but at the same time virtually invisible to us. A black hole weighing perhaps 2 to 4 million times the mass of the Sun. But because of the research that was put into them over the last couple of decades, we've gone from knowing absolutely nothing about them to getting to learn more and more up close and personal. And while things have just gotten crazier, Michio Kaku just announced that we've finally gotten a look at what's inside a black hole. This new information brings light to the details the world of science might have missed all along. Join us as we dig deeper into black holes and unveil what's inside space's big bad. What are black holes? Before we get into the details of what Michio Kaku found, we have to talk about the firsts. Even though most of us have some idea of what black holes are, there are still some gaps in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the concept of black holes was purely theoretical. It took another 50 years for the scientific community to find evidence that black holes actually exist. This happened in the 1960s. They were studying the Cygnus constellation when they noticed an oddly bright blue star that was emitting X-rays. This star wasn't a stagnant object, but was going around a giant black something. Upon further investigation, it was found that the X-rays weren't just moving around on their own, but they were being sucked into the black thing they were orbiting. Thus, the name black hole. This discovery was significant because it provided proof that black holes actually exist and that were just a figment of Albert Einstein's wild imagination. While that was great, it also meant that there was this unreal entity in space that we urgently needed to know more about. So researchers all around the world got to work. This black hole was named Cygnus X-1 and it is located in the constellation Cygnus, about 6,000 light-years from Earth. It was no small discovery. It's about 14 times brighter than the Sun and incredibly dense, which causes it to have a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is called a black hole. The concept of a black hole is both fascinating and terrifying. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, never to be seen again. But that aspect of danger makes it even more necessary to learn everything there is to know about them. Was this it, or were we just beginning? The answer ended up being the latter. After the discovery of Cygnus X-1, scientists started to search for other black holes. They found that there may be close to over 100 million black holes in the Milky Way alone. But because they are so incredibly hard to detect, we still don't have an exact number. Nevertheless, from the looks of it, there are several million black holes in the Milky Way, in our very galaxy, which is what makes them even more important to study. So let's break it down. The main concern with black holes is always going to be gravity. Their gravitational pull is so intense that anything that enters it compresses down astronomically until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the scariest parts about the research that's gone into black holes is the fact that if someone were to fall into one, they would get stretched to the point that they become a single line. This process would happen slowly and the person would die before the final form actually sets in. So let's just say that no one should be stepping into one. But they're all over, so could we really be in danger? Despite the fact that the closest black hole to Earth is 1,500 light-years away, it's still close enough to bring up questions and concerns. In 2021, scientists were able to release the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed several nights in a row, and with each photograph, the researchers gathered more and more evidence about it. They had to stitch the individual photos together to create something that filled all the gaps. This way, they were able to figure out that there are 3 layers to a black hole. It's not just one single gaping hole of nothingness as many people believe. Things are a lot more complicated than that. To even get to the nothingness part of a black hole, you have to make it through the first 2 layers. The first layer is called the event horizon. While in the first layer, it's the point of no return. Once you pass the event horizon, there's no turning back and you will be sucked into the black hole. The 3 layers. It only gets worse from there on out. The second layer is the photon sphere, which is the region where light orbits the black hole. Any light that enters this region will be trapped and will not be able to escape the black hole's gravitational pull. Finally, we come to the third layer, which is the singularity. This is where everything that enters the black hole gets compressed down astronomically until it becomes a singularity. The singularity is a point in spacetime where the laws of physics as we know them break down and we just can't predict what happens next. At the singularity, the density is infinite and the laws of physics as we know them cease to exist. Now, what makes all of this infinitely worse is the fact that every single black hole you study will be entirely different from the last. Sure, they do tend to follow the same 3-layer concept, but the way they function could be vastly different. Now, if this were anything else, all we'd need to do is hop back on those telescopes and just study the problem at hand in detail. But with black holes, you can't really do that. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe like the Voyager inside a black hole is not possible because anything that enters the event horizon is pulled towards the singularity where it is compressed to an infinitely small point. So you can't exactly waste billions of dollars just to get a glimpse every time because the second the probe gets close enough, it'll just crush into nothingness. Because of that glaring problem, scientists are left with no option but to study these objects in a 2-dimensional way even though they are 3-dimensional phenomena in reality. To make matters even more challenging, there are also the 2 problems of every black hole being unique and the laws of physics as we know them breaking down when we try to explore the inside. This means that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that the researchers haven't been busy. There are lots of different theories and explanations of black holes, and well, with each one, things get more and more interesting. Theories. One of the most compelling theories about the formation of black holes is that they are created from collapsed stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star begins to collapse in on itself, becoming smaller and denser as it does so. If the star is massive enough, this process can continue until it becomes a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the core of the galaxy M87. Astronomers observed a superpowerful whirlpool of superhot hydrogen gas that was spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of this spinning disk of gas should have caused it to violently fly apart in all directions, but it didn't. Scientists deduced that there had to be a colossal mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns and could only be a black hole. But that's not the only theory where black holes spin. In 1963, the New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr showed that a spinning black hole wouldn't collapse into a point as previously thought, but to a ring of fire or a thin disk. The disk would be spinning so rapidly that centrifugal forces would keep it from collapsing. This spinning disk of matter is called the ergosphere, and it is the region surrounding the black hole where the laws of physics start to break down. But the most intriguing feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical passage through spacetime that connects 2 separate regions of the universe or even 2 parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of space-time. In Einstein's theory, space and time are not separate entities but are interconnected, forming a 4-dimensional fabric called space-time. Objects with mass warp this fabric, creating a gravitational field that causes other objects to move towards them. Now imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. It's a shortcut through spacetime that connects two distant points in an instant. Wormholes aren't just a sci-fi concept, they are actually a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse almost immediately. But the existence of an Einstein-Rosen bridge would mean that black holes are not just cosmic vacuum cleaners but could also be portals to other regions of space-time. So could we use a wormhole to travel through space and time? Unfortunately, the answer is probably no, not yet anyway. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can travel through spacetime. But even then, the theory of wormholes and black holes as pathways to other parts of the universe or even to different times has been a subject of fascination and speculation among physicists for decades. The idea that there might be shortcuts through the fabric of spacetime, allowing travel through great distances or even into the past, could possibly be revolutionary if we could actually achieve it. One of the most intriguing concepts in this area of study is the Kerr wormhole, which is named after the mathematician Roy Kerr who first described it using Einstein's equations of gravity. This type of wormhole is essentially a hypothetical tunnel through spacetime that could connect two distant points, such as two different universes or even two different times within the same universe. The Kerr wormhole is often visualized as a ring-shaped portal, similar to the looking glass in the story of Alice in Wonderland. Walking through the looking glass transported Alice to a world where animals spoke in riddles and logic didn't always apply. In the same way, passing through the Kerr ring could potentially transport a traveler to another universe or another time where the laws of physics might be very different from those we are familiar with, but at the destination that could just be normal. While the idea of wormholes as a means of interstellar travel or time travel is certainly exciting, as we've glossed over before, it's also a subject of controversy and debate among physicists. Some have pointed out that wormholes, and particularly Kerr wormholes, might be unstable or impossible to traverse due to the intense radiation and subatomic forces surrounding their entrance. The critics argue that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity and not the quantum forces that govern radiation and subatomic particles. In order to truly understand the nature of these phenomena, a new theory is needed that can unite the laws of gravity with a quantum theory of radiation. Throughout the world of science, this is called a theory of everything, a single theory that can unite both Einstein's theory of gravity and the quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for decades. While there are lots of different versions of what this could be, the only one that has shown promise is superstring theory. Superstring theory unites gravity with the theory of radiation. The theory proposes that subatomic particles are actually tiny vibrating strings and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the fascinating things about superstring theory is that as a string moves in time, it warps the fabric of space around it, producing black holes, wormholes, and other exotic solutions of Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with the quantum theory but also explains many of the mysterious phenomena that we observe in the universe. But there's something about this theory that really throws a wrench into how simple it might sound at first, but in a way makes more sense too. The superstring theory requires 10 dimensions of spacetime in which the strings can vibrate. This is quite different from the 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. It's difficult to imagine what these extra dimensions might be like, but physicists have developed some conceptual models that can help us understand. Consider a 2-dimensional pond inhabited by fish that are only aware of the dimensions of length and width. To these fish, there is no such thing as height, and they can't even imagine what it might be like to live in a 3-dimensional world. But if rain falls on the pond and causes ripples, the fish can see the effects of the 3rd dimension even if they can't actually experience it directly. Similarly, physicists believe that we can't see the extra dimensions of spacetime directly, but we can observe their effects on the world that we experience. In particular, the vibrations of the strings in superstring theory can produce waves of energy that travel through the extra dimensions of spacetime. These waves can manifest themselves as particles with different properties, such as mass and charge. In this way, superstring theory can potentially explain all of the particles and forces that we observe in the universe, including gravity. But there is a catch: the extra dimensions of spacetime that superstring theory requires are so small that we can't really study them directly. The most precise measurements that we can make in our laboratories only use the 4 dimensions of spacetime that we are familiar with: length, width, depth, and time. So how can we even know that the extra dimensions exist? One possibility is that the extra dimensions are curled up so tightly that they are invisible to us. Imagine a sheet of paper that has been tightly rolled up into a cylinder. If you were an ant walking along the surface of the paper, you might not even notice that the paper is curved. Similarly, the extra dimensions of spacetime in superstring theory could be curled up into tiny loops or spirals that are invisible to us, even though they affect the behavior of the strings that vibrate in them. Another possibility is that the extra dimensions were more visible at the beginning of the universe during the Big Bang. According to some versions of superstring theory, the universe began in a state of 10-dimensional spacetime with all of the dimensions equally visible. As the universe expanded and cooled, the extra dimensions began to collapse and curl up, leaving us with the 4 dimensions that we observe today. If this scenario is correct, then we might be able to detect traces of the extra dimensions around us. The mathematics involved in superstring theory is incredibly complex. It's opened up entirely new areas of mathematics that were previously unexplored. However, the challenge of solving the problem of a quantum black hole has proven to be an elusive one. While many physicists have tried to tackle this problem, no one has yet been able to do so. Edward Witten of the Institute for Advanced Study at Princeton has called superstring theory 21st century physics that fell accidentally into the 20th century. Last year, several groups of physicists independently announced a significant breakthrough. They found that string theory could completely solve the problem of a quantum black hole, although only in 2 dimensions, not 10. Many physicists believe that it's only a matter of time before someone cracks this problem, given that the equations involved are well defined, if difficult to solve. Until then, it's still too early to buy tickets for intergalactic travel or time-traveling expeditions, at least when it comes to black holes. With all of this, one thing is clear: there are simply too many questions and even more solutions to these problems. Michio Kaku has explained how one would really know what's the real answer to all the crazy theories. He said that it's important to note that the problem of infinite answers isn't unique to string theory. In fact, many great theories have an infinite number of solutions. For example, Newton's laws can predict the motion of various objects from rocks to rocket ships, but you need to specify what it is you're trying to explain before you can predict its motion. These specifications are called initial conditions. Similarly, in string theory, you need to tell the theory what it's describing, but unlike other theories, the initial conditions of string theory are the Big Bang itself. This means that you have to specify the conditions of the Big Bang at the instant it was created, which are currently unknown. There are a couple of ways to approach this problem. One possibility is to experimentally find the initial conditions at the instant of the Big Bang and then let string theory describe how the universe evolves from there. There are already solutions of string theory that describe the evolution of our universe since the Big Bang, based on some reasonable estimates of its nature. This is a significant achievement. Another more ambitious path is to demand that string theory selects its own initial conditions. That one is a little more complicated and less likely too. So, in a way, we've already narrowed things down significantly. But here, Michio Kaku's string theory puts another spin on it all. Maybe the Big Bang wasn't really all that big after all. He says it wasn't a massive explosion as many might think. It also didn't make a loud noise like one might expect from a bang. The Big Bang theory doesn't provide an explanation for what caused the supposed bang or how it occurred, it simply states that it did happen. The truth is, we need a theory that can account for what happened before the Big Bang. This is where string theory comes in. According to this theory, our universe might have been formed from the collision of 2 separate universes, or it could have emerged from another universe, like a baby being born from its mother. This connection between universes is called a wormhole, which is like a tube connecting 2 bubbles. It's possible that we may have already discovered evidence of this umbilical cord that connected our universe to another. In a way, We could just be living inside a black hole this whole time but not know it. Think about it, because we exist in 4 dimensions and can't see anything beyond it, it's possible that we're actually in a black hole, and the black holes we're studying are actually wormholes to these other dimensions. Do you think there could be truth to that theory? Let us know in the comments below. If you like this video, please give it a thumbs up, and we'll see you in the next one.